Go. 3.14 polar function graphs. Here we go.
Now that we have learned and explored how polar coordinates work, it is only natural that we would begin to explore the concept of polar functions and their graphs. For polar functions, the inputs are given by theta, the independent variable, and the outputs are given by r, the dependent variable. On the AP Pre-Calculus exam, questions may use the phrasing below to introduce a polar function. The graph of the polar function r equals f theta, where f of theta equals 3 minus 3 sine theta. Is shown in the polar coordinate system for 0 is greater or less than or equal to theta, and is less than or equal to 5.
All right, fantastic. A lot of the times I don't actually write it like this. I just go ahead and say r equals this. However, your inputs are thetas and your outputs are usually r's, okay? And so they're kind of backwards when we do our polar pairs, okay? It's in r comma theta, but it kind of goes backwards in what we're normally used to. All right, let's keep going.
Graphing polar functions. Creating a table of values is always a good strategy when attempting to graph a new or unknown function. We will utilize this strategy to help us create a graph of a polar function.
All right, fantastic. So I'm not going to do all of these. I'm going to not do a lot of these terms because it's a sine function. And so a sine, do we know like a pi over 4? That's a square root 2 over 2, right? And I don't want to deal with that because I don't want to graph the square root 2 over 2. And I don't want to do the pi over 3's because I don't want to deal with the square root 3's over 2's either. And so why do I keep the pi over 6's though?
So 1/2.
That's just 1/2. All right, I can deal with that one. All right, and so if it's a cosine function, guess what I actually use? I don't use pi over 6, but I actually use what? Pi over 3's. All right, and so that's why I kind of cancel out some of them. All right, so let's do it. And so we're just going to substitute in 0. And so now for this function, sine of 0 is what? 0. And so now we have 3 minus 3 times 0, which is 3. All right, and so now on my polar graph, I'm at 0, and then I go out how much? 3. All right, so let's do it again for pi over 6. And so when I substitute in pi over 6, what's the sign of pi over 6? 1/2. And so now I'd have 3 minus 3 times 1/2. Well, 3 times 1/2 is what? 3 halves. 3 minus 3 halves is 3 halves, also known as 1.5. Okay, I'm going to use a decimal in this case. And so I have pi over 6, and pi over 6 is right here. And so then I go to 1.5. All right, so we're right around there-ish. All right, and so now let's go to pi over 2. And so when I substitute in pi over 2, what do I get? What's the sign of pi over 2?
2, square root 2 over 2. Oh.
0. And, oh, sorry, not 0. All right, sine of pi over 2 is 1. And so now we have 3 minus 3 times 1, which is 0. All right, sorry, I jumped ahead. And so now at pi over 2, I'm at 0. All right, and so right now, I'm kind of graphing like that. All right, and so now at 5 pi over 6, when I substitute in 5 pi over 6, what's that going to be? What's the sign of 5 pi over 6? 1/2. And so then what do I get again? 1.5. And so at 5 pi over 6, 5 pi over 6 is over here, yes? And so now I'm going to go out 1.5. And so now I'm kind of right there. And so now I'm going to substitute in pi. And so when I get pi, what's the sign of pi? 0. And so then what do I get here? I get 3. All right. And so at pi, I'm going out 3. And so now it kind of goes like that. All right. All right, so now let's do 7 pi over 6. And so what's the sign at 7 pi over 6? Negative 1/2. And so now I have negative 3 times negative 1/2, which is what? Positive 3 halves. And so now I have 3 plus 3 halves, which is what? 9 halves, aka I'm going to call it 4.5 for graphing purposes. And so now here's my 7 pi over 6, and now I need to go out to 4.5. And so I'm going out to there. All right, and so now at 3 pi over 2, what's the sign at 3 pi over 2? Negative 1. Good. And so now I have 3 minus 3 times negative 1. So that goes to what? 6. And so at 3 pi over 2, I go all the way down to what? 6. And so now I can go there. All right, good, very nice. And so now I got 11 pi over 6. And so what's 11 pi over 6? That's what? It's going to be the same as 7 pi over 6, which is 4.5. And so at 11 pi over 6, I'm right here. And so now I go out to 4.5. And then at 2 pi, that's going to be the same as 0. So what does it go back to? 3. And so now it completes its shape right there. All right. And so what does it look like?
Heart.
It looks like a heart, and it's very much similar to a heart. It's called a cardioid. All right. This is actually a shape called a cardioid. So on these, what did they create?
Circles.
They created circles. And the reason why is that these coefficients of thetas were 1 and nothing else added to them. All right. That's why they were circles. All right. Now, which ones moved right and left? Which ones moved right and left? The cosines moved right and left because cosine deals with what? X. Love that. And then which ones moved up and down? Sines, because sine deals with what? Y. Well, what does this coefficient out front of my cosine or sine do? It makes it bigger, okay? It stretches it, that's fine. But what is it actually? The what? It's not the R. The R is this whole thing. So that number out front is the what, Aiden?
Diameter.
It's the diameter, all right? It's not the radius, it's actually the diameter. That's how far out it goes, all right? This one, this first set, they are called cardioids, all right? They are technically called cardioids. I'm going to call them butts, all right? Nice butts, all right? And this next set, this 1 minus 2 cosine or 1 plus 2 sine, these are technically called limacons with inner loop. With inner loop. Those are technically the names for it. I'm going to call them buttholes. All right? All right. This next one is technically called a limacon. This technically is called a limacon. And I call those flat butts. All right? And so all of these are in the form of r equals a plus or minus b cosine or sine theta. All right? Now, where is the bulk of these shapes coming from? If I have plus cosine, where is the bulk of them? To the right, because cosine is what? Positive, and it moves with the x. So if the bulk of it is, if it's a positive cosine, the bulk is right. If it's a negative cosine, where's the bulk of it? To the left. All right. Same thing here. If I have a negative sign, the bulk of it is where? Down. And then if it's a positive sign, the bulk of it is what? Up. Okay. Does that make sense? Because cosine deals with what? X, and sine deals with Y. Love that. And so now, what makes them a cardioid or a limacon with inner loop or just a regular old limacon? What makes them that shape? How do I get a cardioid? What do we notice about A and B? They're the same. And so to get the healthy butt, we just have to have A is equal to B. All right? That's going to make that nice symmetrical heart. All right? Now, how do we get a butthole? How do we get an inner loop?
Not equal.
Okay, no, not equal is true, but which one has to be bigger?
The B.
The B, exactly. So if B is greater than A, B is greater than A, you have a butthole. It's an inner loop. All right? You got an inner loop when B, butthole. Get it? All right, cool. Now, this is called a limacon. Limacons don't have loops. What makes a limacon? What makes the flat butt? A is bigger than B. So A is greater than B, and are we cursing in class?
Nope.
No, we're not calling them a-holes. All right? Everybody good here? All right. So the origin in a polar mode is called a pole. All right? So these are called the pole. Which ones are allowed on the pole? The cardioids and the limacons with inner loops. Which ones are not allowed on the pole? Just the limacons. So, how many? Oh, first of all, these are called roses. This is technically the name for it. They are called roses. And each one is called a petal or a loop. All right? And so, how do you dictate how many petals or loops each row has?
Coefficient.
The coefficient of what? Of theta, exactly. And so it's going to just match up with that coefficient of theta. Now, what does this number out front do?
That's how far the petals go.
That's how far out the petals go, exactly. And so this will go out to 3. This one will only go out to what? 2. All right. And so that's its maximum length that it goes out. All right. Let's move to the next set about these. All right. And so these are roses. However, how did we figure out how many petals these had?
Double them.
They had double. Why were they double? The coefficients were what?
Even.
Even. All right. So when the coefficients of thetas are evens, we double the petals. All right. And again, what does this coefficient out front of the sine or cosine do?
Length.
It's the length. Good. All right. That's how far out they go. All right. And so again, doubled when they're even, and they are the same when they are odd.
On the AP pre-calculus exam, polar functions will only appear in multiple choice questions. This means that a student will not be required to sketch a polar function by hand on the AP exam. However, students will be expected to understand polar functions, their graphs, and what portion of the graph exists with various domain restrictions. When working with multiple choice questions involving polar functions, it is advantageous to evaluate the function at several values of theta. Utilizing the multiple choice options can be helpful when determining which values of theta to consider.
All right, fantastic. So remember we're doing the sinusoidal and cosine graphs, all right? Remember I told you to pick a maximum and see if it actually is that maximum and you substitute in that theta. It's the same thing here. And so if we look at this first example, the example 2, we need to figure out what graph this is. Now, how many petals does this have? 3. Does that narrow down any of my answer choices on this one? No. How far out does it go? 3. So does that narrow down any of my answer choices whatsoever? No. And so now we need to figure out which one it is. All right. And so just like before, I would kind of pick a maximum. All right. I would not pick its pole because they're going to touch the pole quite often. We'll talk about when it goes to the pole today. However, I would kind of pick a maximum here. And so where is that one? This is at what theta value? At pi over 6. So I want to try to get theta equals pi over 6. And what do I want my r to be? I want my r to be 3. All right? And so let's kind of go through these choices just like we did for the maxes and mins on our normal ones. All right? And so then if I substitute in pi over 6 right here, 3 times pi over 6 is what? 3 pi over 6, which is also known as pi over 2. And so what is the sine of pi over 2? 1. So 3 times 1 is 3. Is that what I wanted? Yes. And so that's the one we want. Now, I want to do another one just to make sure that you realize that it's not just a every single time. And so if I substitute in pi over 6 here, I'd have at pi over 2 again, right? 3 times pi over 6 is pi over 2. And so what's the cosine of pi over 2? 0. And so 3 times 0 would be 0. Is it at the pole there? No, I wanted it to be at its maximum. All right, so it's very similar to what we've done before. Now it's just polar mode. All right, let's do some more. So on this one, because I taught you how these go, we should be pretty good. What do we have here? We got a boho. How do we get boho? When B is greater than A. All right, so B is greater than A. Does that narrow anything down here yet? No, it doesn't. However, where is the bulk of it? It's down, right? And so what made it go down? Minus what? The sine or cosine? Sine. And so which one does it match up with? B. And so we didn't even have to test any points if we truly understood the shape. All right? And that's why I wanted to go over that stuff before. All right? Let's keep moving. Here we go. So example 4. I need a good reader up in here. Ethan, go for it.
A portion of the graph of the polar function r equals f of theta, where f of theta is equal to -3 sine of theta, is shown in the polar coordinate system for a is less than or equal to theta, which is less than or equal to b. If 0 is less than or equal to a, which is less than b, which is less than 2 pi, which of the following could be values for a and b?
All right, fantastic. All right, and so on these, I kind of like to know where they start, where its maximum away is going to be and like where it's going to come back to the pole. All right. And so if we have -3 sine theta, what really is that? It's a circle. And which way did my circle go? It's going down. And so what's happening is it's actually a circle, but I don't need that left side of this circle. I just need this part. Is everybody following me on this? And so now this is at 0. Agreed? Like 0 is right here, true? And so does it anything start at 0? No, because 0 could technically be over here too if I have a negative radius. Does everybody follow me? So now this is at pi over 2, yes? Do I see anything at pi over 2? No. Now, at pi over 2, it could go back here because this would make it to what? A negative radius. Is everybody following me? And so then I want to try to figure out what happens at pi over 2. All right, I want to see if it's at a pole or if it's down here. So let's substitute in pi over 2. So what is sine of pi over 2? 1. And so now -3 times 1 is what? -3. So at pi over 2, guess what it is? It's at what? -3. So instead there, it's now down here. And so this is where it's at pi over 2 because it flipped. All right? And so now I need to figure out when it goes back. All right? So I need to figure out when it goes back right there. And so I want to figure out when it touches the pole. And so when it touches the pole is when I set it equal to 0. Because at 0, it's at the pole. Because I don't have a radius going out. And so now I divide by -3, which is still what? 0. And so then when is sine 0? At 0. When else? At pi. When else? At 2 pi and so forth. However, this part is at what? Pi over 2. And it's going to go to what? Not back to 0, but at pi. And so it goes from pi over 2 to pi.
Example 5. A portion of the graph of a polar function r equals f of theta, where f of theta equals 3 cosine 3 theta, is shown in the polar coordinate system for a less than or equal to theta is less than or equal to b. If 0 is less than or equal to a, less than b, less than 2 pi, which of the following could be the values for a?
All right, fantastic. So all we care about is this segment right here. All right, that's all that we care about. Now, how many petals is it actually going to have? 3. It's going to have 3 petals. Have 3 petals. However, all I care about is half of that one petal. All right, and so this is where theta equals what? 0. 0. So theta is equal to 0 here. Does everybody agree with that? All right, and so now I'd have at theta equals 0, what do I want r to be? 3. Substitute in 0. So now we'd have 3 times 0, which is 0. What's the cosine of 0? 1. And so 3 times 1 is 3. And so guess where this thing is starting out at? At theta equals 0. All right, because r is equal to what? 3. Now I need to figure out when this goes back to the pole. All right. And so just like the other example, I'm going to set 3 cosine of 3 theta equal to 0 because I want to figure out when it goes back to the pole. All right. And so now we're just going to divide by 3. So I still get cosine of 3 theta is equal to 0. And so then when is cosine 0? At pi over 2. When else? And at 3 pi over 2. And all the other pi over 2's basically, right? And so how do I start solving for theta though? I divide by what? 3. And so theta is equal to what? Pi over 6. All right? And so guess when it goes back to its pole? At what? At pi over 6. And so that goes from 0 to pi over 6. So this figure shows 6 cosine of 3 theta. And then our domain is restricted to pi over 3 to 2 pi over 3. And so I need you to catch this part. So pi over 3 is right here. Agreed? And 2 pi over 3 is right here. Everybody good with that part? However, this is also pi over 3 down there because I could get a negative radius. And then this is also 2 pi over 3 because I could get a negative radius. So really, it's like all of that part and all of that part could be from pi over 3 to 2 pi over 3. All right, let's keep going. And then it says the portion of the graph remains in two pieces. One of those pieces is in the portion from quadrant 3 from C to D. So the portion in quadrant 3 from C to D is this portion right here. All right, so that's the portion that they're speaking of. Now, this could be with this part too. All right, so pi over 3 to 2 pi over 3, this portion could be up here if my radius was positive. All right, then it says, which of the following describes the other remaining pieces? So, do I have any more remaining pieces here? No. However, it could be right here, though. And so my remaining pieces is this portion right there. And so what does that portion cover?
2 pi over 3.
From D to A. And so that's why it is C.